Hello, good morning. Myself, Dr. Shaila Dinkar Apte. Today we will see the details of the Butterworth filter design under the category of infinite impulse response filter, that is IIR filter. This means whenever the impulse is applied as an input to the filter, the output will be lingering for longer time, for almost infinite time. This is the book that I have published with Wiley India publication. You can go through this book for further details. This is the second part of the IR filter design. Under IR filter design, we have already seen that these IR filters, they are designed directly from the analog design. So analog design is well established and we take help of the analog filter design and we just convert the analog filter in the digital filter by using some type of mapping function. So we have considered there are four different types of mapping functions. One is backward difference method, another is forward difference method, then we have impulse invariant method, and we have bilinear transformation method. Those methods we have seen in detail. Now, there are three categories of the filters, analog filters. Those are already in the existence. One is Butterworth filter, second one is Chebyshев filter, and third one is the elliptical filter. So let's go through these filters one by one. In this video, we will see the details of the Butterworth filter. Now, these category of filters called as Butterworth filters, they are characterized by this equation P and omega is equal to 1 upon under root of 1 plus omega raised to 2n for all n greater than or equal to 1. So this is the corresponding frequency response that is specified. So it is a function of omega. Now we can use the Maclaurin series expression and we can expand this P and omega as 1 minus half of omega raised to 2n plus 3 by 8 omega raised to 4n and so on. So using this particular expansion, we can see that the first 2n minus 1 derivatives will be 0 at omega is equal to 0 because the first derivative will be minus half into 2n into omega raised to 2n minus 1. Then again, if we differentiate, we'll have omega raised to 2n minus 2 and so on. So you will have first 2n minus 1 derivatives resulting in a value equal to 0 for omega equal to 0. So we can conclude that the response of the filter is maximally flat in the passband. That means in the passband you will have absolutely maximum response. That means the response will be equal to 1 for the complete passband. So let us consider the low pass filter characteristics. So we are plotting the low pass filter characteristic P and omega with respect to omega. Now, in this case, you will find that at omega equal to 0, the corresponding response, the derivative is 0. That means the response is maximally flat, almost up to the cutoff frequency, and then it monotonically decreases. How we define the cutoff frequency? The cutoff frequency is the frequency for which the corresponding magnitude falls to 0.707 of its maximum value. Here the maximum value is 1. So where the magnitude falls to 0.707 of its maximum, this will give you the corresponding cutoff frequency. As we consider the increasing order, say n is equal to 5, then have n equal to 10 and n equal to 20, you will find that the response becomes more and more flat in the pass band and monotonically decreasing in the stop band. So as you increase the filter order, you get the complete pass band with response equal to 1. That is P and omega is equal to 1. Now let us consider where are the poles of these transfer functions. See, the denominator is, we can write it as 1 upon, it is 1 upon under root of 1 plus omega raised to 2n. Now this 1 plus omega raised to 2n is in the denominator. Now what is this S we can write it as j omega. So S square will be equal to j omega square. So it is minus omega square. So minus s square will be same as omega raised to 2 and then raised to n will give you this equation 1 plus minus s square raised to n equal to 0. Now if you find out the roots of this particular equation are located at the corresponding value of s of k, which are supposed to be the 2nth root of unity because this is 2 s raised to 2n. So to nth root of unity are the roots, and these will definitely lie on the unit circle. These are supposed to be the pole locations and they lie on the unit circle. So the poles we can write it as s of k is e raised to j 2k plus n minus 1. So it is 2k minus 1 has to be there, and plus n, because for the nth value, nth order, we'll have to write it as separately the corresponding poles. Into pi divided by 2n, these are the roots. Let us move ahead. So let us calculate the roots. So let us consider n is equal to 2. That is, the order of the filter is equal to 2. Order of the filter is equal to 2, then means there will be two roots. Two roots where? Two roots on the left hand side of imaginary axis, and two roots will be there on the right hand side of imaginary axis also. So there are four roots, because when n is equal to 2, we are getting four values: k equal to 0, 1. These will lie on the left hand side. For k equal to 3 and 4, these are the roots which will lie on the right hand side. So let us calculate the roots. S1 is equal to, so let us put n equal to 0 first. In the corresponding equation, we can calculate this value for the root. When we put k is equal to 1, we get this root. K is equal to 2, we get this root, and k is equal to 3, we get this root. So we are getting four roots of the corresponding equation. We are using corresponding expression for xk that we have already seen. Right. Now let us plot these poles. When we plot these poles for n is equal to 2, we are getting four roots. This is first root, this is second root, this is third root, this is the fourth root. These two are on the right hand side and these are on the left hand side of the imaginary axis. The poles on the left hand side will have to be utilized to form the corresponding polynomial, because then only we'll be getting the corresponding system as the stable one. With poles on the right hand side, we'll be getting the system that will not be stable. Right. So this is the equation Sk we have to use to calculate these values of the poles. This we have seen. Now let us move ahead. So let us calculate the polynomial equation now. Now, considering the roots on the left hand side of imaginary axis, because this will give us the stable system, the first order polynomial will be just s plus 1. The location of the root on imaginary, first order root, which is first order polynomial with the root on the unit circle, will have the polynomial written as s plus 1. For order 2, we'll have to consider two roots on the left hand side of imaginary axis, and we'll have to write s minus pole 1 into s minus pole 2 and multiply the two. So we'll get s square plus root 2s plus 1. So this is supposed to be the denominator polynomial for the Butterworth filters that we want to design for the practical applications. Now, if we want to design the filter of order 3, then the polynomial can be found as s cube plus s square plus s plus 1. Here there will be 6 roots and we'll get 3 roots on the left hand side of imaginary axis. These 3 roots will be multiplied to get the polynomial. So these polynomials are already calculated and they are already stored and available in the form of the chart. Once we know what is the filter order, we can directly select the corresponding polynomial and design the low pass filter. Let us consider one example. Design a second order discrete time Butterworth filter whose cutoff frequency is 1k at the sampling frequency of 10,000 Hz using BLT method. Plot the corresponding magnitude and phase response. This is the example that we are considering. So with this cutoff frequency that is given, 1 kilohertz, this cutoff frequency is the digital cutoff frequency. We have to first calculate what will be the corresponding analog frequency. So omega d is equal to 2 pi into 1000, that is equal to 2000 pi. Now we calculate omega a as tan omega dt by 2. What is omega dt by 2? We can just calculate 2000 pi into t is equal to 1 upon fs, so 1 upon 10,000, because 10,000 is the sampling frequency. This 2 is there, so you get pi by 10. Now calculate omega a as tan pi by 10, so it comes to 0.325. So this is the corresponding analog frequency for which cutoff frequency for which we have to design the filter. Next step is we have to put this omega, we have to use this omega A and we have to scale the transfer function. The transfer function will, in the transfer function, we'll have to put S is equal to S upon omega A. Now, what is the transfer function for the second order Butterworth filter? The transfer function is Hs is 1 upon S square plus root 2 S plus 1. Now, here, there, wherever there is S, we'll have to put S equal to S divided by omega. So, S divided by omega is 0.325 square of this plus root 2 into S upon 0.325 plus 1. So we can just evaluate this and we'll get this as the polynomial. Okay. And this 0.325 is also supposed to be inside the bracket, which is supposed to be squared. So S will be replaced by S upon 0.325. The whole thing is to be squared, and the square value for this is coming to be 0.1058. Okay, and which is coming again in the numerator. The third step in the design is converting the z domain. So whatever s domain equation we have to put s is equal to z minus 1 upon z plus 1, because we are using bilinear transformation method. As we understand, the corresponding equation for conversion will be linear in the numerator, linear in the denominator. That is z minus 1 upon z plus 1. So we call it as bilinear transformation method. So after putting the value of s as z minus 1 upon z plus 1, and after simplifying, we get this as the transfer function in z domain. So these are the corresponding coefficients in the numerator polynomial. These are the corresponding coefficients in the denominator polynomial. We have to use these coefficients whenever we write down a MATLAB program to calculate the frequency response. So if we want to write the MATLAB code, we are writing Butterworth LPF design using BLT method for this problem 3. First one is clear also, all variables will be clear. Then this B is equal to, that is the numerator polynomial coefficients. So 0.0676 and 0.1352, 0.0676, and A is 1 minus 1.1422, 0.4124. So we are writing the numerator and denominator coefficients in this particular case, and then we write FRAQ command, wherein we are writing FRAQ B comma A. 256 is the corresponding size of the fast Fourier transform, and 10,000 is the sampling frequency. So we can calculate the magnitude response, and this magnitude response turns out to be like this. This is the phase response. You can see that the phase is linear in the passband. The passband is between 0 to 1000. The corresponding response is maximally flat up to 1000, and it is monotonically decreasing in the stop band. But the stop band response is not as satisfactory, because even in the stop band, we are getting some response, and it is not attenuating as per the requirement, as per the desired values for by the user. So in case of Butterworth filter, we can see that even though we get maximally flat response in the pass band, the transition width, as we can call, it is very, very large. And in that case, the corresponding filter order that is required in order to get the corresponding transition width would be very large. So filter order requirement is increasingly large in case of Butterworth filters. Now let us consider what will happen if we want to design high pass filter, band pass filter, and band reject filter. If we want to design high pass filter, the corresponding HS basic transfer function, we have to use it as s square upon s square plus root 2 s plus 1. Then we have to write band pass filter. For band pass filter, we have to write it at W8 upon, Ws upon s square plus Ws plus omega 0 square. And for band reject filter, s square plus omega square upon s square plus Ws plus omega 0 square, wherein the W is supposed to be the bandwidth given by upper cutoff frequency minus lower cutoff frequency, and omega 0 square as the multiplication of the two cutoff frequencies. So this you have to first calculate that, put it in this particular equation, get the corresponding transfer function in S, then calculate omega A. Firstly, do the frequency warping, that is put S is equal to S upon omega A, then you use the scaling, and then you transfer it into the Z domain. same as we have just done to get the Butterworth filter design in the digital domain. Now let us see how the filter order can be calculated. I have told you that in case of Butterworth filter, the order that is required, order requirement would be large. Now in this case, a Butterworth LPF is an all-pole filter represented by the squared magnitude response. This is given by the squared magnitude. This is the squared magnitude response that is written down. Now in this particular equation, omega c is the cutoff frequency, 3 dB frequency. Omega p is the passband H frequency, and epsilon is related to your passband ripple, right? Now, in case of this particular specifications, omega p and omega s, and the maximum attenuation in the stop band will be specified. And epsilon is normally not specified in this case because in case of Butterworth filters, the ripple in the passband is very small. So there is no ripple at all, and the attenuation also is very small. So because it is maximally flat in the passband, so we don't consider epsilon. We consider this equation only for Butterworth filter. The ripple in the passband is not specified as the Butterworth filter is having maximally flat response in the passband. And at omega s, that is the stop band, the magnitude response is 1 upon delta 2 square, where delta 2 is supposed to be the ripple in the stop band. Right. So let us see how the calculations can be done. So at omega s, the magnitude response is 1 upon delta 2 square. So we can write 1 upon 1 plus omega s upon omega c raised to 2n, 1 upon, which is same as 1 upon 1 plus epsilon square, omega s upon omega c raised to p raised to 2n, which is same as delta 2 square. Right. So this is the magnitude response that is specified. So what is 1 upon delta 2 square? It is equal to 1 plus omega s divided by omega c raised to 2n. So we get 1 upon delta 2 square minus 1 as this. And this particular 1 upon delta 2 square minus 1 is what we write it as delta. So here we write it as delta. Then 1 upon delta 2 square minus 1 is written as delta upon epsilon, where epsilon is supposed to be the passband related to passband, divided by twice log omega s upon omega c. So finally we get this equation. Because of this square, these two goes away and we get this equation. So let us see how to find the filter order. So let us consider one example so that it will be easy to understand. So determine the order and poles of the Butterworth filter with minus 3 dB frequency as 1000 Hz and an attenuation of 40 dB at 4000 Hz. So cutoff frequency, that is stop band frequency is 4000, cutoff frequency is 1000, and at stop band the attenuation is specified as 40 dB. All right, because it is attenuation in the magnitude response, we have written 1 upon delta t square, right? So omega c cutoff frequency is 2 pi. This is supposed to be the 2 into 1000 pi, that is 2000 pi. This is angular frequency. Then omega s stop band 2 into 4000, so 8000 pi. Delta 2, that is attenuation in the stop band, is 40 dB, so it is 0.01. So we directly use this equation for calculation of n. Log of 1 upon delta 2 square minus 1 divided by twice log of omega s upon omega c. Delta 2 is 0.01 and then omega s is 8000, that is the stop band h, and omega c is the cutoff frequency 2000 pi. So if we substitute and calculate, we get n is equal to 4, because then value that we are getting after calculations is 3.32. So to meet these requirements, we will consider the value of n which is slightly higher than that we calculate. So if in the calculation we are getting 3.32, we will use n is equal to 4 in